Let's talk about properties of exponential equations. This is from Unit 2 of Algebra 2B. So this is just going to be a good sort of general introduction to some of the ways that we're going to manipulate exponential equations to help us simplify and solve. For more information and for a sort of more robust look at these, make sure you read through the research section of, I think they start talking about it in Lesson 8 of Unit 2. All right, let's get started. So, an exponential equation is something of the form f of x equals a to the x, where a is just some number and x is a variable. Now, you've seen tons of functions that have exponents in them, right? Like f of x equals x squared. This isn't an exponential function though, right? You know this to be a quadratic function. And you've seen things that look like f of x equals x cubed. But again, you know that this is called a cubic equation. An exponential equation, notice that the variable is in the exponent, and that's what separates that class of functions. So we're going to be dealing with exponents that have variables in them. Now, a really useful property about these exponential equations is that if I have an expression where I've got these two bases that are the same, and I've got some exponent b raised to some exponent x, and b is also raised to some exponent y, and the expressions are equal, then I know that the exponents must be equal to one another, right? So for example, if I had 2 to the x equals 2 to the y, well, x must be equal to y. Or, another way of looking at it, if I had 3 squared equals 3 to the x, you could probably pretty easily see, oh, well, x must be 2, right? X must be equal to 2. Okay, it's sort of an intuitive property when you look at it like this. Okay, so let's practice with that a little bit. So the same thing goes, by the way, for logarithms. So if I've got logarithms, and what's not written here is that they have the same base. So if I've got logarithms with the same base, and this result in here is the same, then I know that a must be equal to b, or in the reverse order, if a equals b, then the log of a must be equal to the log of b. And we're talking specifically about when a and b are greater than 0. So to put this in writing, if I had log base 2 of 5, and I said it's equal to log base 2 of d, you can probably see that 5 must be equal to d. Okay, so that's one direction. In the other direction, we could say, well, 4 is equal to y. So that means that the log of 4 must be equal to the log of y. Okay, and again, these are useful properties. I know when you're looking at them at first, it seems like, well, that's great, but who cares? You'll see why they come into play and why they're useful as you're doing your workbook and your checkpoint exercises. So let's do some practice. So say we needed to solve 4 to the x minus 3 equals 16. And these are just our properties that we're going to keep in mind. So say we had to solve 4 to the x minus 3 equals 16. First, rewrite these so that they have the same base, right? Notice that 16 can be rewritten as 4 squared. And the point of doing that is so that I can apply my exponential properties. So now that I've got the same base, I can just deal with my exponents, and I can say, okay, well, they have the same base, their exponents must be equal, so x minus 3 equals 2, and now I can easily just add 3 to both sides and find that x must be equal to 5. Let's look at another one. So this time we're looking at 9 to the 8 minus x equals 27 to the x minus 3. Change colors here. All right, so first step, see if there's a way to make the bases the same. So I see that 9 is 3 times 3. I see that 27 is 3 times 3 times 3. So I can identify, okay, well, this is a situation where I can use 3 as my common base here so that I can eventually apply this property. So first thing I'm going to do is rewrite each side to have the same base. So 9 has been rewritten as 3 squared. 27 has been rewritten as 3 cubed. Alright, so next, let's not get ahead of ourselves. Next, remember our exponent properties. So if I've got 3 squared and this 2 exponent is inside my parentheses, and I've got 8 minus x outside of the parentheses, if I want to combine this, and I distribute the 2, right? So 2 times 8 gives me the 16, 2 times a negative x gives me negative 2x. Likewise, 3 times x is 3x, 3 minus 3 times 3 is minus 9. Okay? So now I've got the same base, I've got everything pretty simple. I can apply my property and I can say, all right, they've got the same base. So if these two things are equal to one another, that means the value of their exponents must be the same. So 16 minus 2x must be equal to 3x minus 9. And then we can simplify from there. And why don't we just run through that for good measure? I'm going to do it up here since we're sort of out of space. So I could add 9 to both sides, which would give me 25 is equal to, and then I could add 2x to both sides, and that would give me 5x. So if 25 equals 5x, x must be equal to 5. All right, so notice how this rather ugly looking expression with just a couple steps very easily simplified to x equals 5. Let's do another one. This is kind of a peculiar one, so we've got log equals 5 to the 2x. I actually don't really like this example, but let's run through it anyway. 5 to the 2x, I think this is actually miswritten. Yeah, let's just leave that. But let's just look at this step. So if I have this expression 5 squared to the 10 equals 5 to the 2x, that 10, I know I cross that out, that 10 is coming from the base 10. Okay, but again, I don't like that example. It's kind of unclear, so we're just going to continue. Really, I just want to practice applying this property is the important part. So I need to simplify this a little bit, right? So I distribute my 2, I get 5 to the 20 equals 2x, and here's where we apply that property. 5 to the 20th power equals 5 to the 2x. So my exponents must be equal. 20 equals 2x, and you can easily see that x equals 10. So I think that's the last example I have of that. Yes, that's the last example I have of that kind. So remember, first step when you get expressions, for example, if you had like 16 to the 5y equals 4 to the 3y minus 7 or something like that, hopefully you can look at these and identify, oh, well, 16 can break down to 4 times 4, or if you wanted to, you could even break this down and have the base be 2, because 16 is also 2 to the 4th, 4 is 2 squared, right? So it doesn't matter if I pick 2 as my base, if I pick 4 as my base, as long as I end up with the same base for both of these expressions, I'll be able to apply that property. Okay, so step 1, rewrite your equation so that each side has the same base. Once you get those same bases, of course, simplify, and then you can just deal with the exponents in order to solve for your variable. A quick reminder, remember that exponents and logarithmic functions are inverse functions and they undo each other. All right, so for example, the log base a of a raised to the x power simplifies to x. A raised to the log base a of x also simplifies to x. Okay, and I know these are a little bit confusing. What I would say is just write both of these phrases down, have them close to you whenever you're doing problems of this kind, because obviously I would much rather work with x than having to work with this kind of ugly monster over here. Okay, so again, my advice is simply to write down both of these little shortcuts. Or really they're inverse properties, right? But I would write down both of these statements just to keep them in mind. Something that I do when I'm identifying them on my own is I'll even just circle it and I'll say, oh, I've got an a raised to the log base a, and I'll just circle the piece and I'll say, okay, well then that means all that's going to simplify and I'm just going to end up with x. Or like this one up here, I'll say, oh, I've got log base a of a, I know that's all going to simplify, and I'm just going to end up with x at the end. So that's something that helps me organize it. Now, had this been written log base a of x to the a, I couldn't have simplified it, okay? If I do my little trick where I circle things and I say, oh, log base a of x, well, that doesn't help me because these need to be the same value in order for this inverse trick to work, okay? So this doesn't simplify to anything. Likewise, if I had a raised to the log base x of a, if I do my little circle trick and I say, okay, a raised to the log base x, well, a and x are two different things. I can't simplify anything. All right, so again, just write down both of those phrases and keep them handy. Okay, a little bit more practice. Say I've got the expression log base 6 of 2x minus 1 equals negative 1. I can rewrite each side to have the same base, and this is a little tricky, right? This is a little tricky, but I can rewrite this. I've got my base 6, right? And then log base 6 of 2 to the x minus 1. So basically, I kind of, in fact, let's erase all this. I rewrote each side to have the same base. So in other words, I took this whole statement and I said, you know what, that's going to be my exponent for 6. So 6 raised to all of that. And then I did the same thing with negative 1, and I said, you know what, I'm going to designate that as an exponent for a base of 6. Okay? And I'm allowed to do that. I'm kind of like working this in reverse. I basically had x equals y, and then I said, you know what, well, if x equals y, then b to the x equals b to the y. And my b in this case was 6. Notice that because I did that, I can use inverse properties. So I very cleverly chose 6 as my base for this rewriting for exponential form because I knew that it was the base of the logarithm. All right, I know it's a little tricky, so let's go through that one more time. Okay, I'm just going to erase and kind of re-explain here. So we've been practicing with this rule that says that if I have two bases that are equivalent and are both raised to exponents, then their exponents must be equal, right? We've done several practice problems with that. Now we're taking it in the reverse order. So I've got this logarithmic expression equal to negative 1. So think of this part of it as being the x equals y part. And I'm just saying, you know what? I'm going to purposely choose, I've got this 6 as the base of the logarithm. So, being clever as I am, I'm going to choose 6 as my base, and I'm going to apply this. So if x equals y, then I know that b to the x must also equal b to the y. So I'm choosing 6 as my base. Like I said, I'm basically just saying, you know what, I'm going to write in a 6 here as the base, and these statements are going to be my exponents. So hopefully you can see why those are equivalent. Now again, my cue to choose 6 was the fact that the logarithm had a base of 6, because now I can get away with applying inverse rules. Just like I was explaining in the last slide, when I'm checking for inverse properties, I like to just do a little circle thing where I say, all right, 6 raised to the log base 6. That tells me, all right, I've got my 6's here, these are equivalent. I know I'm going to be able to use inverse properties here, and that this is just going to drop out, and I'm going to end up with 2 to the x minus 1. So that's what happened on the left-hand side. I used inverse properties, and I ended up with 2x minus 1. On the right-hand side, there isn't any inverse property to apply, so I just actually carried out the statement. So 6 to the negative 1, 6 to the negative 1 is equal to, you can write it as 1 over 6 to the 1, which is just 1 over 6. Okay. So from here, again, you can see why I'm going to be able to pretty easily simplify. So if I wanted to, I could, I guess we will just to kind of even out the question. So 2x minus 1 equals 1/6. I can add 1 to both sides. That gives me 2x equals, what would that be, 7/6. I can divide both sides by 2, and that tells me that x is equal to 7/12. Okay, but again, the important part here was this trick where I saw that I had a log base 6, and I chose to make that my exponent for a base of 6. Let's do another one. I've got log base 3 of 81 minus log base 3 of x plus 1 equals 1. notice that I've got these base 3's, so you can maybe guess what I'm going to do next. I'm going to simplify, or I'm going to combine rather. I've got these separated by subtraction. Because they have the same base, I'm able to combine them as you see here. So I've got 81 became the numerator because that appeared first, and then I'm subtracting log base 3 of x plus 1, x plus 2, excuse me, x plus 2 became my denominator. So I've simplified this to log base 3 of 81 over x plus 2 equals 1. So I've done some simplifying, but I still have more to go. So notice that this was the quotient property, right? So first I applied the quotient property. This was still kind of ugly and I couldn't really do much from here. So next I applied this pretty little property because now I've established an inverse thing going on. So once again, notice that my base was 3, okay? And my base remained 3 in this step. So I said, you know what? I've got this logarithm with this base 3. Here's what I'm going to do. I'm going to treat this log base 3 of 81 over x plus 2 equals 1. That's kind of like my x equals y statement. And I chose a base of 3, and I turned both of these expressions into exponents, okay? Just like saying, well, if x equals y, then b to the x equals b to the y, right? So that's what I've done here. So notice that now I've got this nice little thing happening where I've got 3 to the log base 3 of 81 over x plus 2. Since I've got my 3's here are equivalent, I know that these operations are going to undo each other, and I can rewrite this simplified as, see if we can get it, there we go, 81 over x plus 2. And what happened to our right-hand side? Oh, right, okay. So 81 over x plus 2. You might be wondering what happened to the right-hand side. Remember, we chose 3 as our base, so the right-hand side went from being 1. When 3 became our base, it was 3 to the 1. 3 to the 1 is just 3, right? So that's why the right-hand side is 3. So this is the exponent we had. So 81 over x plus 2 equals 3. We can simplify from here, right? So I could multiply both sides of the equation by x plus 2, and I could simplify from there. I think it's cutting off a little bit, but we get that x equals 25. All right. So again, notice how we ended up using the quotient property, and not only did we use the quotient property, we use this property, which I guess we haven't really given a name to, just that it's an exponential property. And then we used what we know about inverses, right? So we applied 3 different concepts, all to simplify to get this nice little thing that we were very easily able to solve, okay? So that's the last example of that kind we're going to do. Really quickly, I want to just review natural logarithms, which I mentioned briefly, and I'll mention briefly again just as a reminder. The natural logarithm, so the number e is an irrational number represented by the symbol e. Remember, irrational numbers don't terminate. So for example, 1.112579 whatever, right, goes on to infinity. Numbers that just keep going on with no recognizable pattern in the decimal points are irrational. So we represent them with a symbol because it's easier. So just like with pi, right, which is goes on forever and the decimals don't have any sort of pattern, we say, you know what, I'm just going to write the symbol pi, and you'll know what number or what ratio I'm talking about. E is the same thing. E is approximately equal to 2.718, okay? So in the same way, as you know, pi approximates the ratio of a circle's diameter to its circumference, okay? So diameter to circumference, the ratio from, you know, how many diameters could I fit around a circumference is that 3.14 number, okay? So just like that relationship, E also is special. It approximates compound interest. We won't dive too much into that. But because E is so important, so again, this is just kind of a breakdown of when we say it approximates compound interest. So as we increase the frequency that interest is compounded or calculated, the number we get gets closer and closer to E. So If we're just compounding it once a year, we got 2, twice a year, 2.25, 4 times a year, 2.44, every month, 2.61, right? Again, as you're increasing the periods of compounding, notice that it approaches approximately the number e. So, because e is so special, when we work with it, we actually use a different notation, and instead of log, we say ln or ln. You'll hear it pronounced different ways. But whenever you see that ln written, it represents the natural logarithm. So, if we have something written log base e, again, because that number is so special, we don't even write log base e, we just write ln. Okay, so log base e of x and ln of x are the same thing. This is just a shortcut way of writing log base e. So if we're looking at the natural logarithm versus base 10, remember that a logarithm has the common base of 10. So when you see log of x just written out like that, you assume that the base is 10. You'll never see really ln with any sort of base written because we already know that the base, that it's really saying log base e. Okay, so logarithms have a common base of 10 unless another base is written. Lns or natural logarithms have a natural base of e. Logarithms are inverse of exponent. Natural logarithm is the inverse of e. Okay, so just like we were using those inverse properties for logarithms and exponents, you could do the same thing with natural logarithm and e. And what we mean by that is, let's take a look. So we were practicing this, right? Log base a of a to the x equals x. We were practicing identifying patterns like this and then simplifying to get x. We were practicing identifying a pattern like that and simplifying to get x. Same thing with natural logarithms, okay? So ln of e to the x equals x. You might be saying, well, where's the pattern there? Remember, ln naturally has, or automatically has that base of e. So if you wanted to, you could write a base there. I mean, it wouldn't, nobody does it because it's redundant and it's repetitive, right? So ln base e of e to the x equals x, kind of the same thing going on here. All of this nicely simplifies and we just get x. And same thing over here. Once again, remember that since the natural logarithm has a base of e, which we don't write, but I'll write in just for the visual effect, it's the same sort of pattern that you're looking for, right? So e raised to the ln, which naturally has a base of e, will simplify and you'll end up with x, okay? And that would work the same way in practice as our practice problems with logarithms did, okay? So we're going to conclude there. I know that was somewhat of a brief introduction to exponential functions and some of their properties, and I hope you found it helpful. I will see you guys next time.